Hi, everybody. So now we have this idea of an abstract relation, which covers a huge amount of territory. I mean, from things like equals to, I don't know, all kinds of bizarre relations on a set which might not have any natural interpretation. And so what we need to do in order to get a grip on this is to try to separate out the bizarro relations from the ones that seem like they might behave in a kind of a reasonable way. And so what's happened now is that relations themselves become an object of study, and that's what we gain by abstracting the notion of a relation. Now we can just talk about relations and see if we can find interesting properties of relations. And so that's what we're going to do now. This is chapter 11, section 2. And there are really three fundamental properties of relations that we're going to look at. And you have to know these. They're called reflexivity, symmetry, and transitivity. And we're going to look at each of these in turn and look at some examples of them and see how they line up with the properties that we might naturally expect a relation to have. So we'll start with reflexivity. So a relation is reflexive if for all, remember that, let's just start with fundamentals. A relation R is a subset of the Cartesian product of a set A with itself. So it's a relation on a set A. And the set R is all of the pairs of things that are related by this relation. So the relation is said to be reflexive if for all x in the set, the pair x comma x is in the relation. So using the other notation, x is R to x is related to x for all x in the set A. So some relations are reflexive, some relations aren't. The most fundamental relation of all is equality, and that is reflexive because if every element is equal to itself, x is equal to x. So the equals relation is reflexive because x equals x is true for all x in A. It's more or less what equals means. But it's not the only reflexive relation. I mean, we could take less than or equals. And that's reflexive because if A is less than or equal to A, because A is less than or equal to A. Now, that's covered by the equals part. This is true if A is less than A or A is equal to A, and A is equal to A. So these are examples of relations that are reflexive. If we just look at less than, it's not reflexive because A is not less than A. That's false for all A in A, or in fact for any A in A. And this for all is important because some relations may have the property that some x's are related to themselves, but not all of them. So to be reflexive, it has to be true for all. If we, instead of thinking about numbers, we were to think about people, and we were to say that two people, that person 1 is related to person 2, means person 1 is an ancestor of person 2, then that's not reflexive because you're not an ancestor of yourself. And finally, the relation not equals is not reflexive because x not equal to x is false. Right? So it's not equals is also not reflexive. So this is our first fundamental property, reflexivity. The next one is called symmetry, and it's probably what you would think symmetry might mean. A relation R is symmetric if whenever x is related to y, y is related to x. In other words, if xy is an element of the relation, then yx is an element of the relation. So the equals relation is symmetric because if x equals y, then y equals x is true for all x, y in A. Notice the quantifier here is important. You have to, it has to be true for all pairs x and y. And that's what goes wrong with less than or equals, because less than or equals is not symmetric. So because to show it's not symmetric, there exists xy so that x is less than or equal to y and y is not less than or equal to x. In particular, 3, 5. Right? 3 is less than or equal to 5, but 5 is not less than or equal to 3. Now, I should have been careful here. There is an exception to this, which requires us to focus our attention on the set A. What if A only has one element, or is the empty set? So let's assume for the moment here that A is the set of natural numbers. If A were the empty set, or let's say that A is just the set 1, then less than or equals is reflexive, is symmetric, because the only element in R is the pair 1, 1, because there's only one element in the set, and therefore it does satisfy the condition for symmetry. So you have to take into account what the set A that you're looking at is. And if A were the empty set, then R would be the empty set, and it would have this property because whenever you have a for all on the empty set, it's automatically true. Just like if you have an implication and the hypothesis is false, the statement's automatically true. The is an ancestor relation is also not symmetric because if A is an ancestor of B, then B is not an ancestor of A. And the not equals relation is symmetric because if x is not equal to y, then y is not equal to x. And you could imagine proving that by the contrapositive, namely, if y were equal to x, then x would be equal to y. So, because equals is symmetric. And so not equals is another example of a symmetric relation. The most complicated of these properties is called the transitive property. And by the way, where did these come from? They came from looking at lots of examples of relations and for people trying to figure out what properties all these different examples had that would enable them to sort of divide them up into different categories. So it's not like these were sort of handed down as holy writ from somewhere. They're the result of people trying to extract from lots of examples of relations some fundamental properties. Okay, so what is transitivity? Transitivity says that if x and a pair xy is in the relation and a pair yz is in the relation, then you can skip over the y to get xz in the relation. Or written another way, if x are y and y are z, then x are z. So this is a statement about triples. So just to review briefly, reflexivity was a statement about single elements. Symmetry is a statement about pairs. Transitivity is a statement about triples. Equals is transitive because if A is equal to B and B is equal to C, then A is equal to C. And let's assume, as usual, that our set A is the natural numbers here. Less than or equal to is transitive because if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. The is an ancestor of relationship is transitive because if I'm an ancestor of you and you're an ancestor of this other person, then I'm an ancestor of the original person. And finally, the not equals relation is not transitive. And why is that? Well, to show that it's not transitive, we just have to find an example of a triple where xy is in the relation and yz is in the relation, but xz is not in the relation. So, because we have to negate this for all quantifier. And so, how about this? 3 is not equal to 5, right? and 5 is not equal to 3. But if this were transitive, this would imply that 3 is not equal to 3, which is false. So the triple 3, 5, 3 shows that not equal to is not transitive. Okay. So I took took this example from the book. It's described in detail there. You can certainly read it, but I thought I would take a look at the 3 properties for this particular example. So A is the set of 4 letters B, C, D, and E, and R is given by this list of ordered pairs. And let's look one at a time and see if we can figure out what's going on. So let's start with reflexivity. Reflexivity means that the pairs AA are in R for all A in A. So in this case, there are 4 possibilities. You would need to have BB, CC, DD, and EE. Are all of those in the set? Well, BB is, CC is, DD is, but EE is not. So this relation is not reflexive. Because to be reflexive, it has to be the case that for all A in the set, the pair AA has to be in the relation. And that fails because we have one counterexample. So this is a good chance to put all these different ideas of proofs together. Here we're showing that a for all fails by producing a counterexample, a single example that doesn't fit the conditions. Okay, symmetry. Symmetry is a statement about pairs, and we have 4 elements, and the order matters. So how many pairs are there? Well, we have 4 choices for the first and 3 choices for the second element. Actually, that's not even true because we can allow repetitions. So we really would have 16 choices and we could make a little diagram here. But maybe it's easier to sort of see if we can figure out what's going on. So without doing too much brute force calculation. Symmetry means that whenever we have one pair, we have its opposite. So for the ones that have equality, there's nothing to check. If we have BC, we have to have CB, and we do. So these two go together. And if we have DB, we have to have BD, and we do. So those two go together. And if we have CD, we have to have DC, and we do. And those two go together. So remember what symmetry says. It says if AB is in the relation, then BA is in the relation. So we only have to check the pairs that are in the relation. So BC is in the relation, CB is in the relation. CB is in the relation, so BC is in the relation. It's the fact that, for example, let's look at AC. It's not the case that AC and CA are in the relation, but that doesn't say anything about symmetry, because symmetry is only a property about the things which are in the relation. So it is symmetric. What about transitivity? Well, this one is actually kind of a pain to check. Let's do a kind of random experiment. Notice that BC is in R. What about C? Well, CD is in R. And if it were transitive, then it would have to be the case that BD would have to be in R. And it is. But this is far from a proof of transitivity. This is just a check of kind of one case. We could do another one just to see, what about CB? Well, CB is in R, and BD is in R. And so if it were transitive, CD has to be in R. And it is. So we did 2 quick checks, and we didn't have any reason to believe it's not transitive. But if you remember our first example with reflexivity, had we stopped there, we would have said, well, BB is in there and CC is in there, and we might not have found the fact that EE is not in there. So we have to do more. And what do we have to check? Well, we would have to check all triples. And how many triples are there? There are, since there's repetition is allowed, there are 4 times 4 times 4, which is 64 triples we'd have to check. And just to give you an example, if the triple that we had to check was CDE, what would we do? Well, first of all, we would ask, is CD in R? And the answer is yes. And then, is DE in R? And the answer is no. And then we don't have to go any farther, because CD is in R and DE is in R, then something has to happen. But if DE is not in R, there's nothing to check. And we would have to do this for lots of other possibilities. Maybe we could make this more efficient, because it's enough to pick a pair of elements. And so we don't need to consider all triples. We can just consider pairs of these pairs. And we could eventually maybe boil this down into something which is reasonable, but it's going to drive us crazy. However, we can maybe make some sense out of what's going on here by looking at one of these pictures. So this is a picture of the relation that we were just looking at. So it's the way it was drawn was there's a dot for each of the points, B, C, D, and E, and there's an arrow connecting the 2 elements of a pair. So you remember BB is in the set, and that's why, and DD was, and CC was, but EE was not. That's why E doesn't have an arrow going to it. And DC and CD, so you see there's those 2 pairs, and DB and BD, there's those 2, and BC and CB, there's those 2. So how many edges do we have altogether? 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. And if we go back to the thing, here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So every ordered pair is represented by an edge here. And can we see transitivity from this picture? Well, transitivity says what? It says if you can go from one point to another, like for instance X to Y, and then from Y to Z, then you have to be able to go directly from X to Z. There can't be any sort of open triangles. So you see here you can go from B to C and from C to D, and you can go from B to D. And you can go from D to B and B to C, and you can go therefore from D to C. So if you're patient, this diagram may help you to check that it is transitive. And the property that you're looking for is that whenever you have a path joining 2 points, like this one, there's a shortcut which takes you directly where you want to go. And that has to happen, by the way, also imagine if you look here at B and C, if you can go from B to C, and from C to B, let me get rid of this. It's not letting me, it's too fancy for my own good. You can go from C to B and from B to C, and then transitivity says if you can go from C to B and from B to C, you have to be able to go directly from C to C. So you have to have a loop like this. So the bottom line is this is, in fact, transitive. And as the book points out, when you're trying to prove something is transitive, it helps to, to have some kind of a principle here. And I think the principle is that any two consonants are connected. So this set A, B, C, D, and E has one vowel, and everything else is a consonant. And if you left out E, you have then you have three elements, and you have all possible pairs connecting those three elements. And that's why there are 9 right? You have B connected to B, C connected to C, D connected to D, and then you have B connected to C, B connected to D, C connected to B, C connected to D, D connected to C, and D connected to B. So actually, everything is connected except for E. And once you see that, then, so once you know that everything, if you omit, that everything's connected except E is isolated. Then you get transitivity, because you see that if you have, so X are Y and Y are Z, if these are true, then since these are connected, they're both consonants. And since Y is connected to Z, it's also a consonant. And therefore, since all the consonants are connected, you get that X is connected to Z. But there's got to be a better way. Let's look at an example where we can actually prove something, because the relation that we're looking at means something. And the relation we want to use is congruence. So the theorem that we're going to prove, or the proposition that we're going to prove, is that if you fix n, then the relation defined by A congruent to B mod n has all the three properties. It's reflexive, it's symmetric, and transitive. And here A and B are integers. The relation is defined on the integers, and n is a natural number. So let's take this proof one step at a time. So first of all, reflexivity. We must show that for all integers x in Z, x is congruent to x mod n. Let's remember what this means. This means n divides a minus b. Well, this is true because x minus x is 0 and n divides 0. Because after all, 0 is always n times 0, so n divides 0 for any n. Second of all, symmetry. Well, we must show that if x is congruent to y mod n, then y is congruent to x mod n. And the proof of that is if n divides x minus y, then x minus y is a multiple of n, and therefore y minus x is a multiple of n, and so n divides y minus x. So y is congruent to x mod n. And of these three properties, it's usually transitivity which is the most tricky. So we must show that if x is congruent to y and y is congruent to z, then x is congruent to z. And the proof of this, well, we use the definition as usual. So we have that n divides x minus y, so x minus y is k times n for some k. And n divides y minus z, so y minus z is s times n for some s. And now if we add these together, we get that x minus z equals k plus s times n. And that tells us that x minus z is a multiple of n. So n divides x minus z, and x is congruent to z mod n. So congruence has all three properties. And as we'll see in the next section, relations that have these three properties are really fundamental in mathematics. And they're called equivalence relations, and we will look at them more carefully later on.